Welcome back to Avon Rescue. Today we're going to find out how to get the most power out of your Ford Pinto engine. And for cheap money too. Whether you are building a track car or just want to learn how to crank more power out of your engine, you have definitely come to the right place. This is going to be meat and potatoes from here on in, so let's head over to Chris's shed.
Hello again everybody. Welcome to our little Tiger Avon budget hill climb blaster build. This time, engines. Well, let's go through why we're doing it rather than how we're doing it, because this is, as we've always said, this is not a build manual. This is just trying to make sense of the decisions we've made, the bits we're using and why. Most of you will be fully aware this is a 2-litre Pinto engine. Nothing unusual there. It's a later injection block. If you look on the side here, it's got the numbers 205 cast in, which means it's 2 litre, later injection, slightly better head, slightly stronger block. Why are we using this engine? Well, it came for free when I bought the car. Now, it's never been fitted to the car and it had never been modified. This was just a donor engine that the previous owner had sourced to go with the car. Sadly, never got any further with it. So when we got the car back here, I stripped it all the way down, had a good look, and found out it had quite a lot of bore wear, which is not ideal for what we wanted to do. But we want to try and get the most for the least amount of money. So rather than just flogging the old dead horse with worn pistons, took the decision to send it away, get it rebored, plus 1mm, new pistons, new rings. If I tilt it over very slightly, hopefully you can see, all nice and clean and shiny. You can see the hatch marks on the bores. I was very lucky in that it was only the bores that were worn. When we took the crankshaft out, all the bottom end bearings are perfect. They don't need anything at all. So whereas normally when I'd build an engine, I'd always regrind the crank and put new bearings in it just to be certain. On this one, it was so good. And because we're on this budget, I'm happy to wash everything, clean it all up, check the clearances and put it all back together again. So what this means is we've now got a lovely bottom end in good condition that we know is going to work. Everything that needed machining has been done. I've checked the block surface, it's nice and flat, so we don't need to get the block surfaced. Same with the head. Now, the reason we're going the 2-litre Pinto, as I said a moment ago, is it came for free. But the other reason I like these is a lovely torquey engine. Now, when you're new to sevens or you're new to competition cars, a little high revving bike engine sounds fantastic, but you've got to keep the thing on the boil all the time. And then you don't get to learn to drive the car very well. You get to learn how to manage the engine for the first bit. Now, if you can use a torquey car engine, you bypass that because you then got, it's closer to what you would drive on the road. So therefore you haven't got to relearn everything about engine management before you can start. You can pull it out of a corner at 2,500 revs and floor it and it will go. With bike engines, you've got to be up around the 5,000 or 6,000 RPM mark and it's got to be on the buzz all the time. So for people who are new to these, I think a car engine is actually a better choice. Because there were so many Pintos built, they were so popular in all forms of motorsport, everything for them is fairly cheap. Gasket sets are 25 quid. You know, just silly little bits and pieces, everything's available. Now when I did get the engine, it didn't have a starter motor, an alternator, a distributor. It was just a core engine. Now I managed to find a 1600 Pinto in Brandon, very locally to me, for 30 quid, £30. Nobody wants 1600 Pinto engines, but it had everything else with it. So from this budget angle, it allows us to buy a whole other engine to get all the bits we need for no money. And I've now got a spare cylinder head as well. The bottom end is not so much used because it's a 1600, it's a smaller bore, shorter stroke. So not really going to be used for very much, but all the money was in the extras that I got with it. It's given me a spare sump because I've got to shorten the sump on this one to fit in. Spare cam cover, flywheel, clutches, all kinds of bits and pieces. Now, let's go back a couple of steps. When I first did the introduction to this, the whole ethos of the car is to try and build a beginner's competition car for under £2,000. Which means we can't throw money at it. We've got to build it cleverly, and we've got to build it so it's going to be strong and usable. While we're on the subject of money, which is the ever-present challenge in this entire build, throwing money at cars is really easy, and you can achieve something quite magnificent in quite a short space of time if you have the disposable income to do it. If you're just an ordinary working guy that got family, mortgage, everything else, but you still want to go out and play, then you need to do it a different way round. I don't think either of them are better than the other, but sometimes the choices are limited. So what we're doing on this one is I've done a lot of cylinder head modification work because I used to work for Vulcan Engineering many years ago. So I learnt some of the tricks and skills there to do cylinder head porting, which I'll show you later. We're using a downdraft twin choke Weber carburetor on the original Ford Manifold, and we're using a fairly standard cam. So we're not going to be setting the world alight with power figures, but we should be able to be achieving about 130, maybe 135 horsepower if things go well. In a car that weighs 600 kilos, that's doing nicely. That's really fun experiences. So what I'll do is I'll leave the waffle for now, and then we'll do some handheld look around some of the stuff that we've got that's going with the engine as well, and then we'll show you the build up a bit later on. Okay, now let's go carburetor inlet manifold. So you can see there's twin choke, downdraft, Weber. On a standard Sierra, Capri, Cortina, whichever one you've got, inlet manifold. But what I've done, I've actually machined out all the casting marks on the end of the manifold here. I've actually matched the manifold to the head, and we've turned two of the bolts, rather than just being plain bolts, we've turned them into dowel bolts so they'll align it properly. This is all about making the very most we can for no money of the standard Ford components to try and help it breathe as well as it can. Now see on the side of the carburetor, this is a, will that focus there? Just about. This is a DGAV 3336. And you can see that it's got two slightly different size chokes in the bottom here. That's the 33mm side, that's the 36mm side. So it should give us good progressive power. This should make it nice and easy to drive. It looks a bit grubby, but that's been through the ultrasonic cleaner. It's been apart, everything's been checked over, all the jets have been cleaned out. From here, yes, I could get it vapor blasted to try and make it look prettier, but that's more money. More money, more money. It's still got the tag on it. I don't think it's done a huge amount of work because the throttle shafts aren't worn. There's no big slop in any of them. Everything's quite tight still. It did have an automatic choke on it, on the side here, which we've taken off. So there's nothing holding the choke flap still at the moment. Now in 1980s and 90s, an awful lot of stock car boys used to use these carburetors, and I suppose a lot of them probably still do. Because we've got accelerator pump jets in here and we're going for competition work, this hasn't got to start at 7:30 in the morning to take me to work when it's -5 degrees outside. So we can do away with the choke flaps. What it means is that every time you start the car, give it 3 or 4 pumps on the accelerator and then let it warm up before you try and use it anywhere, which is always a good idea anyway. So we'll end up running no choke at all. It can always be retrofitted afterwards. It's only a matter of undoing the screws and putting the screws back in again later if we want to change it back. Now, very obviously, cylinder head. And let's look at what I've done to try and make things work better. The heart of the engine, with a normally aspirated engine, cylinder head and camshaft are all that makes a difference. You can see straight away I've cleaned the casting marks off the inside of the chambers, but I've not tried to make them any bigger or change their design because I'm still using the standard valves. What I have done is an awful lot of porting work. If we look down inside here, hopefully you can see the valve guide there has been completely reshaped. It's come in from the top. And you can see, to try and ease the air path past the valve guide boss. I've also enlarged the valve throat here right out to the valve size. Because this engine is not going to have to do 100,000 miles in everyday traffic, we can afford to run a narrower valve seat. And we can also clean up all the casting marks and all the nonsense inside here. Now, this is not a show head. I've not tried to make it super shiny because usually shiny doesn't make it that much better. But what I have done is underneath here, where it goes around, this is known as the short side radius, and this is where you can get most power gains on most cylinder heads. By making that a lovely gentle radius rather than having casting steps in it, it encourages the airflow around this side of the valve. On this side, the air is already charging up the port, and the moment the valve opens, the air can rush in this way anyway. But if you can increase the airflow around this side, you can actually generate quite a lot more power. Now, the reason Ford didn't do it as naturally part of their engine building is they wanted to leave it as cast. They made so many of these heads that the ultimate power was not their gain at all. So they left it with a big ridge underneath here and a really wide valve seat so that it would last a long time between service intervals and not burn valves out. But the downside of that is it reduces the area for the air to come through, so therefore it's reducing power. Now if I show you the back of the valve, you can see the little machining marks on it, where I've actually reprofiled the valves to make the air path as smooth as possible down here. Because originally there was a great big ridge all the way around the edge. And that was left there to try and increase the width of the valve seat. Again, to make it last a long time. By doing it this way around, we get a much better air path and we get better power output figures. If you're running forced injection, turbo, supercharger, whatever, none of this is valuable at all, because you're not relying purely on atmospheric pressure to push the air in. And on the exhaust side, again you can see I've reprofiled the valves to try and make them as smooth as possible on the flow in. I've not done quite as much work on the exhaust port, because obviously once the combustion event has happened, you've got a lot of pressure inside the cylinder, and the moment the valve opens, it can help push the burnt gases out. But on the inlet side, the only thing that's making air come in here is the difference between cylinder pressure and atmospheric pressure. As the piston moves down, it decreases the pressure inside the cylinder, and effectively we like to think of it as sucking the air in, but it's not. It's just creating a pressure differential, and the atmospheric pressure is blowing the air in. I'm absolutely intrigued to get this on a dyno when it's built, to find out how much of this basic level theory converts into real world horsepower. And I'm a bit odd in that the maximum horsepower figures don't do it for me. It's where maximum torque is and how long it lasts. That's the bit that makes a car drivable. If we can pull it into maximum torque around the 3,000 RPM mark and hold that till about 6,500 or 7,000 RPM, that's when you get a really exciting car. See, the head surface is a little dirty, but I've checked it with a straight edge. It's all nice and flat, so we're not going to get the head surfaced. We're going to rely on a decent gasket to give us a good seal. Right, now let's have a look at flywheels. When we were talking earlier about bike engines versus car engines, about how they rev, the bike engine revs really well. It's got a very small flywheel and it hasn't got to pull a huge amount of weight around. So therefore they don't need a big flywheel, because Granny's not going to take it to the shops and try and stop it stalling when she pulls out the junction. So therefore they can run a very light flywheel. It makes the engines very responsive. Now this one on the right here, stock Pinto. This is another Pinto one, the one I've modified a little bit. If I turn them over, I know this one's filthy, it doesn't matter. It's only going to end up as a doorstop. And you see this here, there's a huge great chunk compared to this, where the chunk's gone. Now this was all about trying to create lots of inertia in the engine. So if you're pulling away a heavy car, you can let the clutch up quite quickly, and the energy stored in here will help you get over that first pulling away moment, stop the engine stalling so easily. So I've got a pair of scales set up here, and if we pop this one on there, you can see 9.2 kilos. That's the unmodified one. Now if I pop the modified one on there, .7 kilos. So 4 kilos difference. Doesn't sound a great deal, does it? But the difference it makes of that engine being able to rev cleanly and quickly is massive. Trying to reduce any weight from reciprocating parts is a good idea, but losing 4 kilos is huge. Where it comes into its strengths the quickest is when you're trying to down change, when you want to rev the engine before you can change down coming into a corner. With this is going to rev more like a bike engine now. You'll be able to put your foot down and it'll be instant, and the revs will just come up. It means you've got to be a little bit more careful pulling away to stop it stalling, but because we're only pulling the little Tiger at 600 kilos, we haven't got the same problem as you had in the Ford Sierra. So we've gone a lot lighter on the flywheel. We'll find out ultimately how much it's affected the balance of the engine. Normally when I do this kind of thing, I would get the whole of the engine balanced as well. But cost prohibits us doing it that this time. So we're going to take a bit of a chance, see what happens. These are both standard Ford clutch covers. This is the one that came with our donor engine. And if you have a look at the tips of the fingers here, you can see there's quite a flat section along the top. This is quite worn. That's where it touches the release bearing, and it's worn it out through use. Now if we have a look at this disgusting thing here that's covered in surface rust, you'll see that the tops of the fingers are lovely and rounded. So even though this thing looks awful, it's had very, very little use. And if we turn it over and have a look at the thrust face, again, no big ditches and grooves or anything else. So it may seem like a weird thing to choose, but I'm going to use this one. I've got a really nice de-rusting compound, which I can soak this in, which will get rid of all that, and it will come back up like a new clutch again. Whereas this one, the thrust face is okay, but you can see where the clutch disc was stuck to it because it's been sat engaged for so long. I had to pry the clutch disc off with a screwdriver. Now then, let's have a look at this sump. Now if I come around the side, you see I've already cut the top off, and I'm down by about 40mm here to the bottom of the sump plug. And we've cut it off nice and square all the way along. I've stripped the paint off, so I'm ready for welding. There's nothing unusual here. And then what I've made is this nice piece of 2mm thick steel, going to sit on like this. That's going to give us a nice flat bottom and a nice little lead-in ramp. So if we do get off and get in the kitty litter or get on the grass, we've got a little bit of a skid plate there. And then we've got cardboard templates for 2 side infills. Okay, now because I've moved what was effectively that corner forward to here and given it more of a ramp, I've put about 3/4 of the volume of this back in again. So with this and then running the oil level just a little bit higher inside, we should be more or less where we were before. Time will tell. I'm going to have to put some baffles in the bottom of this as well, because with a longer flat area under hard braking, the oil can all surge forward. So I'm going to put some V-shaped arrestor baffles in here, probably 2, one just behind the pickup pipe and one further forward. And they won't go all the way to the sides. They'll leave about a 10mm or 15mm gap down each side. That'll allow the oil to flow back round comfortably back to the pickup pipe, but it will stop it under hard braking from all surging. I'll show you a bit more of that when we get down to putting those in. Right, now the next phase on the sump. You remember me saying a little while ago about a dodgy old 1600 engine I bought just for a few spares? Well, the block has come in really useful, because I can now bolt the sump down onto this spare old block, weld it all up knowing that the sump isn't going to distort, because the block will hold it nice and straight. And I can leave it bolted to the block while it's cooling off, and that should hold everything nice and straight. I've done the oil pickup pipe modifications, which was much easier to do while there was no bottom on the sump. And I've now got 8mm clearance between the bottom of the sump and the pickup pipe, which should work just nicely. So there's the plate. It's going to go on. And there's one of the infills that's going to go in there. I'll show you a bit more when it's all together. Here we are with a bottom and one side tacked in place. I'm going to get the other side, then I've got a good while finish welding. Alright, this is the end result, all finished welded on. So from here, I've still got to fit the drain plug, which rather than going on the bottom, is going to go on the back corner, just here, nice and low. So if we do hit anything on the bottom, it's not going to take the drain plug out. Once I've got that in, I've then got to leak test it, find any pinholes and weld those up. Then it's time to fit the anti-surge baffles inside it, which I can show you in a little while. We're going to use a whole load of plasticine for doing that, to find out exactly where the oil pickup is and make sure we get them in the right place. So hopefully that'll do all we need it to do. And here we are, this is what the baffle plate looks like inside. The whole idea is that under braking, all the oil wants to surge forwards. This diverts it and slows it down. And you've got 2 big recharge slots in the corner, so the oil coming back from this direction can get back past it easily, but it slows it down going in that direction. And in the back corner here, we've now got the sump plug in. It's not going to be quite as efficient as Ford's original design, where the sump was at the very lowest point. But if you imagine when you're changing the oil on this car, you've got the front jacked up anyway. So it's going to be sitting up at that kind of angle. So there's going to be very little left in there, so it'll do the job nicely. So the last job on this now is leak test and then a coat of paint and it can go on. Here we go, we've got all the crappy old paint stripped off. I hate doing that job, bloody paint stripper, it's so messy. Anyway, that's all stripped off now. New bits are all welded on. Looking nice and shiny. And then the cam cover I've done at the same time. Coat primer. And I can get some gloss black in a little while. Quite a bit of work in doing just that. But it's going to be worth it. Okay then, here we go. Here's our finished up, bolted up engine. Just about ready to go back in the car. As I said at the beginning, I'm not going to try and show you how to build a Pinto engine. That's been done many, many times by people far cleverer than me. So all we're going to do is just a bit of a recap of what we've done and why we've done it. So we've got our shallow sump on here, which has been shortened up to give us more ground clearance. We've got a ported and polished head with reprofiled valves. We've got a lightened flywheel and a brand new clutch on the back of it. Still got the trusty Ford Type 9 5-speed. The block was rebored to 2.1 litre and with new pistons and new rings to give us a bit of extra capacity because the block was worn. So what that effectively is going to do, because we've gone up in capacity to 2.1 litre, it increases the swept volume inside the engine. And as a natural component of that, it increases the compression ratio because the combustion chamber volume stays the same size. So I've actually worked it out and we've now got a compression ratio of about 9.75, 9.8 to 1, which is really nice, friendly for pump gas. That should work exactly where we need it to be. When you start getting up to 13 or 14 to 1 compression ratios, which you can do, you've got to be very, very careful of detonation because it'll eat pistons if you get it wrong. And also you need some fairly exotic fuel. We should be able to run this on E5, maybe even E10 without too many problems. In standard form, 2 litre Pinto should put out just over 100 horsepower, 105, 108, somewhere around about there. With the changes we've made, with the better flowing on the head, we're going to run a 4-branch tubular exhaust manifold, which comes from Tigers, which will help the gas flow a lot. We've got our ported inlet manifold now, twin choke down draft Weber Carb. We should be up to about 120, maybe 125 horsepower if things have gone really, really well. I'd be intrigued to get it on a dyno and find out. As far as the standard parts of the engine, we've now got an electronic distributor rather than the points one, just to give us a bit more of an accurate spark. We've obviously got new timing belt, new water pump, all the bits that would normally cause aggravation if you ignored them. So the very next job for this now, get it back in the hole, start hooking it up. We've got Newark coming up this weekend, so it's a bit of a thrash to try and get everything together to make the car look presentable so we can get it there and it won't look like a completely unstarted kit. It should look like it's about halfway through. And then we can have a chat about what you think about it. If you can get the chance to come to Newark, please do. If you're seeing this after Newark, sorry you missed it, maybe next time. So this will wrap up our engine series quite nicely, our engine episode, not series, sorry. So yeah, I'll get it back in the car and then hopefully we'll see you at Newark and we can do some brainstorming from there, see which way it thinks to go. So, alrighty, so I'll leave that with you for now and hopefully I'll see you next time.
Thanks, Chris. As usual, that was fantastic. We learned a lot and it was great to see how simple tricks can make a big difference. There's never a dull moment in Chris's shed and we hope you enjoyed this episode. Chris has been working like an absolute maniac, getting the Avon ready for presentation at the Newark Kit Car Festival. 7 Spot will be there too, so please stop by and say hi. We'd love to have a chat and get your impressions on the build. Thanks for watching. We hope you enjoy what we do at 7 Spot. If you do, please take a moment to smash that like button and subscribe so that you won't miss a single episode. Cheers, and we'll see you at 7 Spot.